everyone. So, welcome to a new conference of the Frontiers of Physics series of the Institute of Harvard Affairs for Theoretical and Computational Physics here at the University of Granada. And today I have the pleasure to introduce Professor Hugo Touchette, who is right here, a good friend and a great scientist. He has been visiting us for 1 month here at the Statistical Physics Group. Professor Touchette made his PhD, he finished it in 2003 in Montreal, right? Okay. Then he moved to Queen Mary University at London, where he became a senior lecturer up to 2014, no, I guess. And then at that time you moved to Stellenbosch University in South Africa, where he's now a professor of applied mathematics. So Professor Touchette is a leading expert in the field of large deviation theory, and he wrote a very influential review on the statistical physics approach, the large deviation approach to statistical physics, and it's the topic that Hugo will explain us today. So Hugo, thank you very much for being here.
Thank you. Should I be on the stage or down? No, no, okay. It's a bit high. Thank you for the introduction, Pablo. Thank you also to Carlos and Pablo for the hospitality for this month. It's been a pleasure to visit. It's a very nice place. I really enjoyed my time. Thanks for coming this morning. The goal today is to give you a kind of introduction to this theory, large deviation theory, and how we use it to study statistical physics, so many particle system. Actually, the people in Granada are very active in that field, and then I'll mention a bit of the research that they do and also the research that I do. So it's got an interesting history, and then I'll go over this. So large deviation theory is really used as a kind of framework, theoretical framework for making sense of statistical physics. And what's interesting and what we've learned over the years is that it's a theory that we can use for equilibrium system, but also for non-equilibrium systems. So we're using the same theory for describing two very different types of system, and that's very the appeal of the theory. But it's not a theory that we invented recently. It's something that it's been lying around, and in fact, the history goes back to Boltzmann. It seems like everything goes back to Boltzmann anyway, but so my goal today is to give the story of that theory and how it came to be associated with statistical physics, how it started. And what's interesting also is that it has two different sets of roots in physics and in mathematics, and it's only in the 80s actually that those two roots came to be merged. And then people realized that what they were doing, they were working on the same theory. So there's lots of work on the mathematical side, which is what I'm showing here, starting from 1938 with the work of Cramer, and then I'll mention that. And then in the 80s, actually, this Ellis made a connection with physics, and then another bunch of people also made connections between maths and physics. So it's a very interesting history, and this is what I want to describe. So I'll start with a bit of history, then the basics of the theory, and then I'll just show briefly how we apply this to describe equilibrium systems and non-equilibrium systems. And the themes that the kind of buzzwords that will appear is that we're trying to describe systems that move with some randomness, but we'll be describing typical states and fluctuations around those typical states. And that these are really the theme that are common to equilibrium and non-equilibrium system. You always need to have many components, like many particles in a system, and then we'll see that what we see has something very deterministic at the macroscopic level is coming from the microscopic randomness, and this is really the theme of statistical mechanics and the stuff that Boltzmann really put forward. Okay, so I'll start with the history. Yes. Okay, so as I said, it starts with Boltzmann. So I think there's a bit slow here. Okay, if you talk to someone in maths actually about large deviation theory, they'll say, oh, large deviations started in 1930s, 1938. But actually, if you're aware of physics and the beginning of statistical physics, you realize that there's a specific calculation that Boltzmann presented, which is really the genesis of large deviation. And this is the calculation. This is the paper, 1877. This is a very important paper in statistical physics. It's the first paper that showed the notion of entropy, statistical entropy. And the idea of Boltzmann is really the idea of statistical physics, is that you're trying to describe the state of many particles. And then for simplicity, he actually considered particles having a discrete number of states, and that was before quantum mechanics, right? So this is quite surprising to begin with. So you have n particles, and they have different energy levels. So for the particle 1, you can specify in which energy level it is, and then you can do the same thing for the second particle, third particle, and the n particles, and this will define the microscopic state of the system. And the idea of Boltzmann, really, that's the genesis of statistical physics, is to say that, well, macroscopically, we don't see these microscopic states. We see something macroscopic. And so what we should be looking really is something like the energy distribution. So the number of particles in some level J, and then we should see something that is very typical at that level, but that comes from the microscopic randomness. So what he calculated then is you want to calculate the number of microscopic configuration that gives rise to a certain energy distribution. And that's what he calls the complexion. And then for this particular system without interaction, this is just the combinatorial factor. So if you have a given energy distribution, you take the n factorial, and then you just take the product of all the occupation levels, and that's the combinatorial factor. You can put the log, and then you can approximate this in the limit when n goes to infinity with the Stirling approximation. And what you get is really the sum of occupation log occupation, and that's the statistical entropy. So that's the first calculation leading to the statistical entropy. I'm showing here actually the excerpt of the paper. M is the entropy, and then you have WLW. L is the log for Boltzmann. And then he uses the Stirling approximation, but doesn't call it the Stirling approximation. Didn't have that name at the time. And what is important, the conclusion is that if you look at the number of microscopic states that are associated with a given energy distribution, you see that you have an exponential number. This is what it says, right? Because I take the log here, and it's proportional to the number of particles. So if I put back everything on the same scale, then the number or the probability of seeing a given energy distribution then will be exponential with the number of particles. And then we'll see later that that's really the property of large deviation. That's the defining property of large deviation, but also it's the defining property of statistical physics as a whole. Numbers, the number of complexions, so the number of microscopic states consistent with the given observation is always exponential with the number of particles or the volume. And so if you look at the probability of observing something, it's also always exponential with the number of particles in the volume. So that's 1877. It's an amazing paper to read, first because it's near impossible to understand the paper in the first place, so you need to read it again and again and again, but it's a very deep paper. And then for 1877, with the notion of probability, very little notion of probabilities that people had at the time, this is a very prescient paper. Okay, so the next bit in the history is Einstein. So Einstein, the idea of Einstein at that point, not related to relativity, but his work in statistical physics, is try to generalize Boltzmann. The calculation of Boltzmann was done for independent particles. You just do the counting. And so Einstein is thinking, can we generalize this argument for real systems that have interactions? So, and can we generalize this not just for the energy distribution, but for any kind of macroscopic variable that you can measure? And then we call this now a macro state. So what we want to calculate is the number of microscopic states that are consistent with an observation of the macro state. Okay, so this could be like the magnetization, this could be like the energy, but it could be also the energy distribution. So you're measuring a given value of that microstate, and you want to calculate the number of microstates that are consistent with this observation. Now, if you don't have a model of the system, you cannot calculate this, but Einstein postulated physically that this should be exponential. So the density of state should be exponential with the number of particles or the volume, and then the exponent that should come there, if it has to be consistent with thermodynamics, it should represent the entropy. So this is what we call Einstein's postulates. Instead of trying to calculate the density of state, you postulate that the density of state always has to be exponential with the number of particles. And then with this postulate, Einstein showed that then you can rederive thermodynamics. So this postulate is consistent with everything that we know about equilibrium system. It means that the probability of seeing a given value of the macrostate will also be given by the probability, and then the equilibrium will be the most probable state is the state that will maximize the entropy. And so that's the principle of maximum entropy that was known already at the time. So I put also the bit of the page where you see this. This is the density of state. It's a constant times the exponential. And then from this, you can derive statistical physics. So this is really important in the history, and then the idea again that we see that probabilities or density of states have this exponential form with the number of particles or the density of states. So that's the start in physics, and then now I'll go into mathematics. So in maths, the first work, and that's really what mathematicians will consider the first work, is the work by Cramer. This is also interesting from a completely different point of view. Cramer was interested in insurance, so he was doing actual mathematics. And then the idea here is that you have a kind of sum of random variables that represent actually claims that people will submit to an insurance company. And so the insurance company needs to know the statistics of these claims. And so you have a given sum here of n claims, and then for simplicity at the time, they would consider the claims to be independent and distributed with the same distribution. And what's dominant at the time in the 30s was the central limit theorem, the fact that all sums should have a Gaussian distribution. But for an insurance company, this is not good. You need to have information about the tails and then going beyond the Gaussian, because you really need to insure yourself as an insurance company against the very large claims that will ruin you. So you need to have more precise information about the distribution of the sum, and so this is what Cramer did. And what he showed is that the full distribution of the sum will have an exponential form with the number of random variables that you have in the sum, and then he could actually find out, so this is the dominant term in the distribution, and then there's a kind of series expansion for all the corrections. And so you see again this exponential form, and this function, which is basically the exponent related to the distribution, is what we call the rate function. So we'll see this function again. And Cramer actually showed in that paper that the rate function is the Legendre transform of the cumulant function related to the random variable. So essentially you have this distribution for the random variable. This is the generating function. I'm missing the log actually here. So this is the cumulant. This is the lambda k. K is a real parameter. If you take the Legendre transform of this, you get the rate function. And the rate function is describing the full distribution of the sample mean as a function of n. And again, if you know the exponential and you look at everything, these are all sub-exponential factors, so you can forget about them. And then to a first approximation, the good approximation of the distribution will be this decaying exponential with the number of random variables. So that's very general. And this is for IID random variable. This is an interesting paper. It's written in French. It's a preceding paper. I've actually translated this in English on my spare time, so it's on my website if you want to read this. It's really an important paper for probability theory because it's the start of probability theory going beyond the central limit theorem. And it goes beyond, and this is why we call it large deviations, is because instead of looking at the fluctuation close to the mean, which will be described by the central limit theorem, you can describe now the full distribution in the tails, so you're describing also the large deviations, and I'll come back on this. Unfortunately, not much happened from 1938, and then we had to wait quite some time before someone picked up the problem again. And the next bit in the history on the mathematical side is some work by Sanov, 1957. Here, the idea, we'll see, is very close to Boltzmann. So Sanov considered a sequence of independent random variables. And think about like 0, 1 random variables, so random bits. And so this is what I'm putting on the slide here. And Sanov was interested in calculating the statistics of if you throw a number of bits on the table, you can calculate the number of zeros that you see and then the number of ones that you see. So that's the histogram of the sequence of random variables that you put. You can throw another sequence and then you'll see a different numbers of zeros and a different number of ones, right? So these two numbers here are random, so this is a random variable. In fact, if you put them together as two components, you have a random vector associated with a given sequence of random variable. So the question is, what's the distribution of that random vector? And in the paper, Sanov just says, well, if you consider discrete random variable, you can do the combinatorics of it. This is the multinomial distribution. You can use Stirling to approximate it. And then you get that the probability of seeing a given histogram of zeros and ones actually goes exponentially with the number of random variables, the number of bits that you have. And then the decay is described by this little exponent, which is the relative entropy. And this is really funny when you read it because you think of Boltzmann. If you know Boltzmann, you think, well, Boltzmann did the same calculation basically 80 years before. And what's more interesting is that in the paper of Sanov, he says, oh, we can also apply this to continuous random variable. What we do is that we coarse grain the continuous random variable, and then we take the continuum limit, and then we get this limit, the sum will become an integral. And if you read the Boltzmann paper, he has the same argument too, because at the end of the paper, he considers the perfect gas with the continuous velocity, and he says, how can I apply my counting technique? I'm going to coarse grain the velocity, and then I take the continuum limit. So the parallel is like really strange and quite interesting. But there's really no connection. There's no citation to Boltzmann and Sanov paper, and there seems to be, at that time, no knowledge of him about what was known in statistical physics. So this is the bit in the paper in Russian. You can find the English translation of this, translated by the US Army, actually. Interesting. And then out of this, again, you see the exponential form, and then you see that everything decays exponentially. And then out of this, you can also get what's the most probable distribution that you'll see. If you throw zeros and ones on the table with the same probability, 1/2, 1/2, if for a very long sequence, you know, of course, that the most probable frequencies that you'll see will be 1/2, 1/2. But this tells you exactly what the probability of this happening. It says that this is exponentially likely, and so anything else is exponentially unlikely. So if I throw a very long sequence, I'm going to see nearly for sure a fractions of zeros, which will be nearly equal to the fraction of ones. Okay, and this is really important. Anything else, I can throw a lot of sequence, but I would need to throw an exponential number of sequence in order to see a departure from this typical value, and this is really important. Okay, I should say, if you have any questions, you can stop me. I'll be happy to answer questions like anytime or at...
This is related to Shannon.
Yeah, this is related to Shannon completely, and Shannon actually took this when he wrote the famous paper on information theory, actually used this result, and it's everywhere. In information theory, this is called the asymptotic equipartition theorem. So I'm not going to make the connection, but there are strong connections with information theory. Now, after this, not much was done, and the subject in maths only came up again in the 70s, at end of 70s and 80s, with papers that I'm going to discuss afterwards. But already you see two different streams of history and two different sets of results that had no connection, and then what I want to discuss is how they are connected. So what we know now in the modern theory is that large deviation theory is really something that applies to random variable in the abstract sense, mathematical sense, but as an application, you'll take random variables that have physical significance. But in abstract form, the theory is about a kind of random variable which is parameterized by some n. N can be the number of random variable in a sum. It could be the number of particles in a system. So n is whatever it is, but it's just defining a sequence of random variable. And then the goal is to obtain the distribution of that random variable. And the expectation is that the distribution will have an exponential form. So we actually define this as a definition. So we're going to say that a distribution satisfies the large deviation approximation, or we say satisfies the large deviation principle, if to dominant order of first approximation, the distribution decays exponentially with that n. And the meaning of that n, again, will depend on the application. I'll show you examples where the n is not the number of particles or random variables. It's something else. Okay, so this is how I would write it in physics. Of course, if I give a talk in maths, I won't use the wiggle symbol. So what's the meaning of that wiggle symbol? It means that if I take the log of the probability, then the dominant term will be linear with n, and anything else will be small corrections with respect to n. So there'll be small o corrections to the main dominant term that I have. So if I divide by n on either side and I take the limit, this will disappear, and all that I will retain is this rate function. So when you have an approximation like this, if you say that the dominant term in the approximation of the distribution is an exponential, it means the same thing more or less as saying that this limit exists and gives you the exponent. Okay. And already you should see a similarity with the way we define thermodynamic functions, and I'll come to this. Okay, and so this is the large deviation limit, and that's the meaning of the wiggle sign, and then the exponent you get is what we call the rate function. So anything in large deviation will be described by this rate function, and so the goal is to show that for a given random variable, a given stochastic process, for instance, you have a large deviation principle or a large deviation approximation for the distribution or the density of the random variable that you're considering, and the goal really is to get the rate function. So I show here a kind of a picture of what's happening when n goes to infinity or when n increases. Because of the exponential behavior, you have to have a concentration because the rate function we'll see is positive. So whenever you increase n, you actually dampen the tails quite a lot, in fact exponentially. And so and the way that it decays really will be given by the rate function. So we'll see that the rate function is positive in general, and then in many cases, in most cases, it has a 0. And the 0 will be the place where the distribution itself does not decay. So if the rate function is positive, then the distribution has to decay exponentially. So if you take n larger and larger, then it has to concentrate by conservation of probability to a place which has to correspond to the 0 of the rate function. So the rate function gives you information about the tails. We'll see this, but it gives you information also about where the probability will concentrate when n is very large. And the approximation is very good when n is large, which is really the kind of range that we consider in statistical mechanics. And for us, n going to infinity will correspond to the thermodynamic limit. Okay, but I'm already jumping ahead actually about what I want to say. Okay, so this is just a definition. We're expecting distribution to have an exponential form, and the goal for us is to show that this is indeed the case and then to get the corresponding rate function. So how do we do this? So there are many methods in large deviation theory, and I don't want to explain everything. I'll just show you the main method that I use actually in practice, but I think that many people use in the field to calculate rate function, which is a result known as the Gartner-Ellis theorem. And the result is based on calculating actually something like a dual function to the rate function, which happens to be the same function that Cramer considered before. And the idea is very similar to, instead of looking at the distribution itself, you look at the Laplace transform of the distribution or the Fourier transform of the distribution, which is something that we do all the time in physics. Instead of looking at direct space, look at Fourier space. So this is what we're going to do here. So the random variable is an, and here I'm going to take an exponential expectation of that random variable. So this is what we call the generating function, but it's really a Laplace transform of the distribution of an. This bracket there is just the expectation, the mean with respect to an, and I have the n there. I take the log, so this is a cumulant generating function, and because of the limit, we call this a scale cumulant generating function. And this is my lambda k. K is the real parameter. And so the goal in the theorem is to calculate this function without knowing, of course, that you have a large deviation principle. And so this is the theorem. So the theorem, essentially, I'm simplifying here, but it says that if lambda k exists and is differentiable, then you have the two things you're looking after. You have a large deviation approximation for the density, so for this random variable, so the distribution will behave exponentially with n, and then the rate function will be the Legendre transform of that lambda k. Now, you might not recognize here a Legendre transform, but this is really a Legendre transform. It's what we call a Legendre-Fenkel transform. If I want to calculate the maximum of this quantity, I'll just take the derivative with respect to k, and then you get exactly the equations that you will consider when you consider the Legendre transform. And so I of a is the Legendre transform of lambda k. And so this gives you really a handle on calculating a rate function. What you do is that you have the random variable, it's defined in a given way. We'll see some examples. You try to calculate this lambda k. In many cases, you can do this. And then you check that it's differentiable. If that's the case, you have the LDP, and then you have the rate function. Okay, so here's an example. Let's go back to the case of Cramer, where we have now the random variable is a sample mean. So it's a sum of n random variables, simple case independent random variables distributed with the same distributions, so they're independent and identically distributed. I take the 1 over n to have the concentration, and then in this case, I need to put this in the definition of lambda k, and it's a simple calculation to show that if you put the sample mean, which is IID, then everything simplifies and the limit actually disappears. And so what you're left with is lambda k being the simple cumulant, just like Cramer. So essentially, the Gartner-Ellis theorem, which is a very general statement about general random variables, if you apply it to IID sample means, you recover Cramer. And so the prediction is that the density of this, of the sample mean, will be exponential, and the rate function will be the Legendre transform. So as a particular case, you can take Gaussian random variables. In this case, the cumulant is easily calculated. It's a parabola. It's differentiable. I can calculate the Legendre transform of a parabola. It's also a parabola. So this will be the rate function. And this is interesting because for a sum of Gaussian, the rate function is a parabola. So it predicts Gaussian fluctuations, which is consistent with the fact that the sum of Gaussian is Gaussian. So it has a zero. The zero is the mean. So the distribution of the sum will concentrate on the mean. That's the law of large number. And then around this, you have Gaussian fluctuation. But for a sum of Gaussian, everything is Gaussian. So the rate function is quadratic. If you take another example now, if you sum a bunch of exponential random variables, then you get a rate function. You can do the same thing. This is the cumulant function. It's differentiable. You can take the Legendre transform, and then you get this function. So here I'm showing the rate function. And so from reading the rate function, I can tell what the distribution looks like. So it has a zero. It has a concentration point, just like the Gaussian case. That's the law of large number. But now the rate function is not a parabola. It's actually asymmetric. So you can predict that the right tail will be different from the right tail. Okay, and in fact, this is asymptotically linear. So in the tail, the very large deviation of a sum of exponential is also exponential. So I can read this from the rate function. And this is kind of the game that we play in large deviation. Now you can try to find what's the exact distribution, but you'll be working a lot to realize that really the dominant term is an exponential. Okay, so if the theory was only applicable to independent random variables, it wouldn't be a theory as such. And so what happened from the work of Cramer and the work of Sanov is that in the 70s, 60s, 70s, people started applying this to Markov processes and stochastic processes more generally. And so there are two streams actually of results. One is what we call the Freiden-Wenzel theory, which is you take a differential equation, you have some Gaussian noise to it, and so you end up with a stochastic differential equation. And now there's a small parameter, and that's the amplitude of the noise. So you're looking at the limit when epsilon goes to infinity. And in this case, this defines also a large deviation limit. Instead of taking n to infinity, you take epsilon to 0. Here you see that all the probabilities related to this, so for instance, the probability of reaching a certain state x at time t starting from some other state x naught at time 0, this behaves exponentially with the noise amplitude, so it's 1 over epsilon, and so you have a large deviation approximation, and this is the rate function. The rate function will be given by the minimum of some action. And this is a theory actually that is also interesting because it was also discovered in physics independently by Onsager and McLuhan in the 50s. And this is a theory now that we use to describe transitions between different thermodynamic states, but also like in chemistry, for instance, if you shake a system or you heat a system, you can trigger a chemical reaction. Well, that's an escape that's exponentially unlikely at low temperature. So this is what we call Cramer's transition theory. So thermal activation, nucleation actually is all described by this kind of system, and there's a lot more applications that we consider now. But the idea is that all probabilities are exponential. There's just exponential with another parameter, which happens to be the temperature or the noise amplitude. Another application that we consider now in physics is something that came from the 70s from the work of Donsker and Varadhan, which is large deviations. Essentially what you're trying to do, large deviations of sum of random variables, but you drop the independence property. So the random variables can be actually related by a Markov chain, or you can look at, instead of a sum of random variables, you take an integral of a random variable, but it's a function of some stochastic process, a Markov process. In this case, you can show also that in many cases, the distribution of this random variable follows a large deviation approximation, and now the large parameter is the integration time. So everything behaves exponentially with t, and then the lambda k you can calculate, and it happens to be related to the spectrum of some linear operator. So there's a strong analogy actually with quantum theory, because you need to do a spectral calculation in order to do the prediction, in order to get the rate function. So this is something that we use a lot in physics now to study what we call stochastic thermodynamics, or the thermodynamics of non-equilibrium systems that are kind of small but not too small. So molecular motors, biological systems, and also systems that carry currents. And so I'll show this there. Here the picture is the same, but now instead of taking n to infinity, you take the integration time to infinity. So you have concentration, and that concentration will be described by this rate function. Okay, so this is just a kind of panorama of the theory, has it developed, and the mathematical content of the theory. And here again are the basic ideas. Everything is based on the idea that the random variables that you consider have distributions that behave exponentially with some parameter. And so this is the picture that we showed before. And what's important to note is that the rate function can be very complicated. So I showed cases where the rate function is a kind of convex parabolic function, but it can look a bit like this, where you have this rate function. But the idea, again, is that out of looking at the rate function, I can say a lot about the shape of the distribution. Essentially, the rate function is like the log linear plot of the distribution, right? And so it captures the scaling of the distribution. So if I have a rate function like this, I'm going to say, oh, this is the concentration point, but there's another point that's quite likely, but less likely than the concentration point, although it's more likely than other points. So this will be a kind of metastable state. And so you can imagine that we can use this formalism to describe phase transition and metastable state, but you would still have a concentration here at that point. And the concentration is exponential, so it means that you have a lot of microscopic states or configurations for the random variable to actually realize these typical values exponentially. So everything is exponentially probable, meaning that the fluctuations will be exponentially improbable, unlikely. Okay, so I've mentioned that the typical values of the random variable is related to the law of large number, and that's because the distribution concentrates there in the limit, and that's really the law of large number. Locally, in many cases, the rate function might not be a full parabola, but you can do a parabolic expansion around the minimum, and so this will predict Gaussian small fluctuation, and this is related to the central limit theorem. But in general, and this is really the contribution of the theory, is that the fluctuations are not Gaussian, encoded by the shape of the rate function. Okay, so now what I'll do, so this is the theory. What I want to do now is to show you how we can apply this to equilibrium systems and non-equilibrium systems. And the case of equilibrium system is a bit funny because essentially we're trying to rewrite everything that we know, but in the language of large deviation theory. And then the question that I get a lot is, but why doing this? We already have a theory of equilibrium system. What's the point of rewriting the theory with large deviation? And my answer is that it adds precision to the theory because now we can use mathematics to predict when we expect to see some behavior or some other behavior, because now we have the backing of a mathematical theory. It's a bit like saying, well, I can do general relativity without knowing differential geometry as a mathematical theory, but it's clear that general relativity, really the fundamental basis of it is differential geometry. So I would claim the same for equilibrium system. So the picture that we have in mind is really the picture that everybody knows this, is that we have n particles and then we have the microstates and the macrostates, right? In English, it's a bit difficult to make a distinction between MI and MA. So it's the microstate and the macrostate. So Spanish and French actually will be superior to this now. So you have the microstates at the level which is not what you see. What you see as an observer is the macroscopic variable like the magnetization, the energy. And so you want to calculate the distribution of your observation at the level of the macro state, and this will be the sum of all the probabilities of all the states that lead to a given observation of the macro state. So you need a kind of probabilistic model for your system, which happens to correspond to what we call an ensemble. An ensemble in statistical physics is just a specification of a probability distribution onto the microstates. So the problem that we want, that we're considering in equilibrium statistical mechanics, is implicitly to find a distribution for macro states. Out of this, of the distribution, you can locate the most probable states, which will correspond to the equilibrium states, and then we can study also fluctuations around those equilibrium states, and then we do everything in the thermodynamic limit n going to infinity. Now, one reason why we consider n to infinity is because we want thermodynamic properties that don't depend on the shape of the system that we look at. If I want to calculate the temperature of the table, it should not depend on the size of the table or the shape of the table. And so the thermodynamic limit actually includes this. You calculate specific quantities, so quantities per volume, quantities per number of particles as opposed to full energies or things like this. But another reason to actually consider the thermodynamic limit is because in that limit, everything has an exponential form. So if I look at the microcanonical ensemble, which is the ensemble in which all the states having a certain energy have the same probability, I can calculate the probability of a certain macro state, and according to Einstein, this will be proportional to the entropy. Now we know that the entropy is extensive, so it goes like the number of particles, or it goes like the volume. And so if you actually use the physical principle of extensivity, you end up with the statement that all probabilities will decay exponentially with the number of particles or the volume. So this is just a reinterpretation in terms of large deviation concepts of what we know already in statistical physics. So in this case, the probability will be parameterized by the energy because that's the control parameter. But this is really the probability that you can calculate with the microcanonical ensemble. And the prediction is that the probability will behave exponentially with the number of particles with a certain exponent, which is essentially the entropy. It's minus the entropy. So the rate function in this case is minus the entropy. You can take a different ensemble, for instance, the canonical ensemble, where now the control parameter is the temperature. Same thing here again. We know physically that probabilities will be the exponential of the free energy. That comes from Landau theory. Again, free energy is extensive, so this is consistent with probabilities behaving exponentially with the volume or the number of particles. You have an approximation. This is not exact because extensivity is only a limiting property, so you get the corresponding limiting property that distributions are only approximately exponential. But again, that's the dominant term in the distribution. So you have exponential concentration of observables, meaning that whatever observations you do, you'll see a typical value that's exponentially likely, and everything else is exponentially unlikely. And this is really what we call an equilibrium state. So if I look at the table, the fact that I see everything microscopically in a very stable way in a given state is really coming from this exponential concentration. If I look microscopically at the table, I would see the atoms actually moving. There's some kind of thermal motion. So there are energy fluctuations. There would be energy fluctuations, but these at the microscopic level are exponentially unlikely with the size of the table. So you have exponential minus n, and you have to think that n is 10 to the 23. So this is an amazingly damped and peaked exponential. Okay, so again, these are familiar concepts, and I'm just rewriting this in mathematical terms. And again, what I would claim is that you get precision out of this now because we have techniques coming from large deviation theory for calculating these rate functions, which means that we can use these techniques to calculate entropy functions. And then when you do a bit of sorting and then cleaning the house a bit, you see that many techniques that have been devised in statistical physics for calculating entropies actually are exactly what mathematicians were using for calculating rate functions. So the analogy is strong and I believe useful. Okay, I have an example, but I think I'm going to skip this example. It's the Maxwell distribution. So you look at the velocity distribution of a perfect gas, and this is very similar to Sanov. It's very similar to Boltzmann. What you see is that you have a most probable energy distribution or velocity distribution that you get, which happens to be the Maxwell distribution. So the most probable state, in this case, the most probable distribution of velocity is the Maxwell distribution. So this is just Sanov theorem applied to a very specific system. What I'll finish with is I'll show you how we apply the same formalism now, but to study non-equilibrium systems. So this is the kind of research that we're doing and the kind of research that's being done in Granada and the statistical physics group. So in this case, when you look at non-equilibrium system, the dynamics is really important. So you're not looking just at a static system with a static distribution corresponding to an ensemble. You have to define a stochastic process. You have to define a dynamical model that will include all the physical interactions, but also the noise sources, thermal noise, and whatever. So you have to devise a model which can be a model for one or many particles interacting. You have to include the external forces, the reservoir interactions, which could be a heat reservoir, a particle reservoir. And the classic case in non-equilibrium systems is kind of a current in a system. So you have a reservoir of many particles, you have another reservoir with a lower chemical value, and so there will be a current of particle actually established, and if you play with the reservoir, if you make them macroscopic, then there will be a sustained current of particles. You can do the same thing with energy. If you have two heat baths, cold and hot, then there will be a current, of course, from hot to cold. But this is all also stochastic. If you look at the microscopic levels, there'll be some noise, and so some kind of noisy behavior, and so you could have a probability of having particles moving the other side. Or if you have a heat current, there's a certain probability that the current actually goes from cold to hot. What's the probability of this happening? So you can model this, and what you realize is that probabilities also behave exponentially. So here you have to now change the ensemble by what we call a path distribution, because you want to describe the microscopic state of your system, which are the trajectories, the random trajectories of your system, and they observe up to some time 0 to some time capital T. And then everything you will observe actually will be function of trajectories. So you really replace those configurations that you had for equilibrium by trajectories for a model representing a non-equilibrium system. But the problem is the same. The goal is to find the distribution of the observable. And you want to find the typical values of that observable, namely the values that maximize the probability, and you want to study the fluctuations also around typicality. And you can do this using large deviation theory by taking thermodynamic limits, but now more general limits like infinite size system, infinite observation time, but also the noise going to 0 like I've showed before. And so this is what we do. So I'm not going to show you like a specific calculation. Well, I'll show you a specific calculation. This example, it's a very simple example, but I think it's a good one actually to get the idea of what we're doing. So this is a simple example where you put a glass sphere in water, just a small one, like a micron-size bead. And because of thermal motion in the water, you have Brownian motion. So you can observe actually with a good microscope the glass bead, and then it undergoes Brownian motion. And what people do now is that they can shine lasers onto this, and then you can control the position of that bead. The physics is not so complicated. You have two counterpropagating lasers, and then you effectively actually create a potential that the particle is trapped in, and then you can move this. So this is called a laser tweezers. I think there are laser tweezers at this university. Yeah. Okay, so how do we model this? Well, you have thermal motion, and then you have mechanics. So this is a noisy Langevin dynamics, or a noisy Newton equation. So you have Newton's equation. This is the friction of the surrounding media. This is the viscous friction. You have the force here, which I'll take to be a kind of linear force coming from the laser interaction. And then you have the thermal noise. That's the noise of the water, the surrounding environment. And now you can do many experiments. You can actually pull the particle, say, with a constant velocity, but the particle is moving randomly in a potential, right? So it can move with the force, or it can move against the force, so you can do positive work or negative work. So all the mechanical or the thermodynamic quantities that you can measure actually will be fluctuating quantities, so they are random variables. So for instance, I can calculate the work done by the laser onto the particle, and I can separate that work into a potential energy that the particle will actually take versus some heat that will be released in the environment. And each of them, so this is of course like conservation of energy, but now conservation of energy for random variables. So this is a random variable, random variable, random variable, and so we call this stochastic thermodynamics. And the question is, okay, there are random variables, so what is the distribution of these random variables? And so with the model, you can do the calculation. It's a spectral calculation, and then you can extract the rate function. In this case, actually, the rate function is a parabola, so it's not so interesting, but the rate function of the heat is not a parabola. So this is quite interesting, but with the techniques from large deviation theory, you can make prediction on the distribution by obtaining the rate function in the limit when t goes to infinity. So you have to imagine that you're doing an experiment, you're doing a kind of typical amount of work on the particles, but there are unlikely fluctuations that are exponential with the time that you do the observation. So it's exponentially unlikely, but it's still possible for the particle to actually run backwards, even if you pull it in the other direction. Okay, so people do this a lot with this kind of experiments, and I've applied this in biological systems. And then the idea again is that you need to define a stochastic model representing your non-equilibrium system. You have some quantities of interest that play the same role as a macro state that we have in equilibrium statistical mechanics. And the goal is to find a distribution, but at the exponential scale, in the limit where some parameters goes to infinity. And this can be applied in many, many cases, for instance, for the current carrying system. And so this is kind of work that's done here in Granada, where you look at current carrying system, but you look at them in some macroscopic limit to actually come up with a kind of noisy field evolution. So you can build field theories that are good models of non-equilibrium systems that will include noise, and all predictions actually will lead to large deviation approximation. So I'm not going to say a lot on this. I'll finish just with a panorama of kind of applications that people have looked at over the years recently. So the main one has been particle transport. So looking at systems that carry current, but stochastic currents, and calculating the probability that you have forward currents versus the backward currents. People have looked also at turbulence, transport of particles with turbulent flows, and also recently weather models. So there's been some prediction about the kind of large rare events of, for instance, really hot temperatures and then global warming. But for instance, there was a big hot spell in France. I think it was 94, no, maybe more recent than this actually, 2017. And then using some models, you can predict actually what will be the probability of another rare event of having a very hot summer, with the probability of this recurring in the next 5 years or the next 10 years. And so people actually study this a lot. And then there are more applications for systems that are out equilibrium, like glassy systems, chemical networks, or chemical reactions that are driven from the outside. And there are more mathematical also applications that people have looked at. So it's quite an active field. There's different groups actually working on this. And what I find interesting again is that we have the formalism actually quite settled and precise, and it makes the thinking actually more precise. And so we can even talk to mathematicians because we're using the same language. And so a lot of the models that they study, we get interested in this, and then vice versa. So there's lots of interdisciplinary work on this. And the work that I'm involved in these days, and this is also the work that a lot of work has been done on this in Granada, and then Carlos and Pablo work on this, and this is a bit of the reason why I'm here actually, and why we had that connection to begin with, is on doing simulations of these rare events. So if you have systems that have this exponential concentrated probability, you still want to understand the tails, which are exponentially concentrated. So you need to devise kind of Monte Carlo simulations of these systems that will be quite clever, because if you just simulate the system on its own, you're not going to see the rare events. They're exponentially unlikely. So over the years, we've come up with different techniques actually to reweight the system and then try to see rare events as typical events. And these are, we can use these simulation techniques or numerical techniques to actually numerically calculate rate functions. So there's only, as you can imagine, only a limited number of systems for which you can calculate analytically those rate functions and make predictions using tools of large deviation theory. So we need numerical tools like we use in statistical physics and physics in general to actually calculate or make predictions about rate functions. And so there are many techniques that we've been using over the years. So splitting and cloning. So this is some work that was done here and then still being done here in Granada. And then there's some other techniques called importance sampling. And there's lots of machine learning tools that are used now actually to do this, because you need to represent really high dimensional functions. So it makes sense to use neural network, for instance, to do calculations. So I'll finish on this. This is a kind of, I always present this at the end, it's a kind of translation table between maths and physics about the concepts that we use and the analogies that we have, which makes this large deviation formalism a good framework for statistical physics. So what we call a random variable really in physics is related to what we call an ensemble or a stochastic process if you consider a non-equilibrium system, and the most probable value will be an equilibrium state for an equilibrium system or a typical state for non-equilibrium systems. Fluctuation is the same as rare event or a large deviation, and the main point I want to emphasize again is that we saw this, a rate function really is the analog of an entropy. An entropy function really is mathematically a rate function, nothing more. A cumulant function is a free energy. I've shown this, but I haven't really emphasized this. And the important bit is that everything has to be done in some scaling limit. This approximation, this exponential approximation, is seen when you have a limit. So either the number of particles going to infinity, the observation time going to infinity, or the noise amplitude going to 0. You can combine those two. You can have a many particle system that you observe over a very long time, and so you can trade off these scaling limits. And these generalize the notion of a thermodynamic limit. Okay, so if you want more details, then Pablo mentioned the review that I wrote some years ago. Actually, I'm close to 20 years now. Something I wrote when I was a postdoc, and then something more recent on Markov processes and non-equilibrium systems. These are lecture notes that I wrote for summer school, and then you have more papers on the website if you're interested. And this, thank you for your attention.
So I saw some papers that call about nonequilibrium potential, and it's exactly the same.
It's exactly the same.
They use a noise parameter, work with this parameter from some mechanical equation at the end of the day. They make this limit. Is it the same?
I would say it's the same. Yeah. So, of course, I mean, in statistical physics, it's been a long-standing problem of generalizing equilibrium statistical mechanics to study non-equilibrium system. And then the first idea was to generalize the notion of thermodynamic potentials to non-equilibrium system. And then lots of work was done on that. If you, in a sense, if you read that work again, but with the lens of large deviation theory, you see that these are rate functions. Yes, yes. So this is what I find interesting. And I think we've come to that understanding also now. I think there's a kind of consensus that that's the case now.
Is that research being done on non-Markovian processes consistent with memory?
Again?
Is that research being done on non-Markovian
yes.
memory?
Yes, there's some work, not a lot. So I mentioned the Markov processes. So these are the kind of processes that we use a lot for modeling non-equilibrium system for different reasons. One being that it's just, they're easier to work with. The maths is easier. If you look now at systems that have long-range memory or memory effect, then it's more difficult. It's also more difficult to even define what non-Markovian is. So you have different models of non-Markovian, and so. But some people have looked at this for non-Markovian model. I did some work also many years ago on non-Markovian random walks. But you can apply the same thing. The difficulty is actually to calculate this lambda k. How you calculate cumulants.
I only wanted to ask you again, or wanted to ask you to explain again the logic behind proposing the lambda function you introduced us to before.
The lambda function, where it comes from?
Yeah, to see if the one variable follows a distribution.
Yeah, there are different ways you can see this. So that's the idea of the Gartner. So if I understand the question, like what's the meaning of this Gartner-Ellis theorem? This one here.
Yeah.
Why I would consider this? So it's a kind of consistency argument. If I look at the expectation of something like this, so this is a generating function. So I'll do the integral over the distribution, and I will take nka. Right. Now, if you expect the distribution to be exponential, then you'll have something like this. Right, so I'm just assuming now, actually, that I have a large deviation principle. And now you see it's an integral that involves everything is exponential with n. So I can put the exponents together first, but it has the form of what we call a Laplace integral, or you can do a saddle point approximation or Laplace approximation. And when you do the approximation, what you get is that this actually, if I put the plus sign, will be Ka minus I of A, but I need to take the maximum over all the values. Okay, so if the distribution behaves exponentially, then the generating function will also behave exponentially with the max. And so the Gartner-Ellis theorem is basically the converse of this. And then what they've done is just to say, from the knowledge of this exponential scaling, what are the conditions needed to get the rate function? Okay, so you just go the other way. But it's a consistency thing. If the distribution behaves exponentially, then all generating functions will behave exponentially, which means that this limit will give you something. Yeah. And so the Gartner theorem is just inverting the logic of this, getting the rate function out of the lambda k instead.
So when you use Gartner series, is the complexity of lambda important in any way?
The complexity or the...
Complexity of lambda.
Oh, yes. So by definition, the lambda is always continuous and it's convex by definition. So it cannot be too complicated. But you could have like corners, you can have some funny behaviors actually at the level of lambda k, and they're related to phase transition. So the analytic properties of lambda k, they will be similar to the analytic properties of free energy. So if you have phase transition, you'd have some jumps and derivatives and things like this. And then we study this also in an non-equilibrium context, and then we call this dynamical phase transitions.
I was just about to say before that it's also very nice from that proof of the Gartner theorem that you will learn the Legendre transform, which is the basis of the dynamics.
Yes. So I remember my first course of thermodynamics, and then you see a Legendre transform. It's like, and then you've seen one in Lagrangian mechanics too, right? The Hamiltonian is the Legendre transform of the Lagrangian. And so you're like, as a student, like, but what's the connection and why do we have a Legendre transform? And my professor at the time just said, no, this is physics. Physics says it's the Legendre transform, it's physics. And then it's only when I started reading about large deviation theory that I realized, no, it's not physics. It's the saddle point approximation. It's the Laplace approximation that comes from the thermodynamic limit. That's why you get the Legendre transform.
Landau used to say that if the knowledge of humanity disappears, what's the main idea you want to keep? You want to pass to the next generation. N is very large.
N is large, yes. Yes, yeah.
Huge amount of particles making matter.
No, we don't realize how much of a concentration it is. I've mentioned like the exponential, and n is 10 to the 23, right? So it's an exponential of an exponential. This is amazingly concentrated. It's crazy concentrated, like, but this is the world we see, and that's the stability we see out of the randomness. So what we call emergent determinism is really the exponential at play.
Okay, so any other question? No? But not, let's thank you again.
Thank you.